Hey everyone, my name is Reese Levine, and on behalf of my co-authors, I'm here to present our paper SafeRace, Assessing and Addressing WebGPU Memory Safety in the Presence of Data Races. So let's first start off with some highlights from this paper. So what we did is we identified what we call a specification vulnerability in WebGPU. And what I mean by that is that WebGPU tries to maintain some high-level safety properties, but its specification actually, when you read it closely, is not strong enough to prevent valid implementations from violating these safety properties. And specifically in our case, that's memory safety. So even though a current implementation may not expose this vulnerability, it's possible that it could in the future. So that's why we call this a ticking time bomb in WebGPU. So we performed several threat assessments to determine the susceptibility of different GPU frameworks to this vulnerability. And we found in the low level that there were actually valid memory safety vulnerabilities in GPUs from AMD and Apple that we reported to the vendors, and we got a CVE from AMD, for example. And we also found potential issues in a pre-release version of the Firefox web browser that we reported to Firefox and was fixed by them. To fix this vulnerability in the WebGPU specification, we introduced and formalized what we call the SafeRace Memory Safety Guarantee, or SMSG. And we evaluated the performance of our fixes, like how much it affected performance of programs on 10 important benchmarks. And we evaluated the adoptability of our proposals on 21 different compilation stacks for 81 hours using fuzzing on various browsers like Chrome, Firefox, and Safari and Edge. I don't have time in this talk to go over all of the details of our work, so I'm going to specifically focus on what the specification vulnerability is in WebGPU and how we fix it. Before I get into the details, I think there are a few high-level insights that I hope people kind of take away from this work. The first is that accelerator support in security-critical environments comes with new opportunities and also challenges. For example, WebGPU is an interface that's exposed by browsers to users to write low-level GPU code, and of course, browsers have very high security requirements. The second is that maintaining the types of safety guarantees that we need when composing languages is a pretty important problem. WebGPU does not generate assembly directly, rather it interfaces with native frameworks which have their own specifications and compilers before you actually get down to the code or the assembly that runs on the GPUs from different vendors. And I think this problem is actually not specifically GPU focused. There's a lot of interesting kind of new work on layering different types of languages, and I think this kind of applies to all of those as well. Okay, so let's actually get into some of the details. What is the specification vulnerability? So first, what is memory safety? Memory safety prevents behaviors such as out-of-bounds access or use after free, and of course, it's been the cause of many, many famous vulnerabilities. So if we look at this example program here in WebGPU Shading Language, or WGSL, we have two memory regions, I and M, and then we have one thread, and all it does is writes I of 0 equal 2, does some independent computation, and then indexes M by I of 0. So this index into M is a potential out-of-bounds access if I of 0 was greater than 3 here. So when WGSL compilers output native language code, they actually just clamp the accesses. So here you insert a min check to make sure that you can't read out of bounds of M. However, in these native languages, you have optimizing compilers. And these optimizing compilers might notice that I of 0 is set to 2 in A, not changed, and then used in B. And it might realize that this min check is actually not needed. So when you generate GPU assembly code, that min check could be removed. And this works fine in this example because we only have one thread. But of course, when you go into multi-threaded scenarios, you have to deal with things like data races. So a data race is an unsynchronized, i.e. you're not using barriers or atomics, and you're accessing the same memory by multiple threads. And this behavior is kind of given undefined semantic in many native GPU frameworks, following the example of languages like C++. So if you look at this example over here, we've added an extra thread, which writes I of 0 equal to 4. And you might see the problem here. The compiler might still notice that I of 0 is set to 2 in a thread local context, so it can still remove the min check. But of course, when you actually execute this on the GPU, it's possible that you interleave A, C, then B, and you get an out-of-bounds access. So this is the vulnerability. It's a conflict between WGSL's memory safety requirements and the optimizations and specifications of lower-level frameworks and their compilers. And it's not that WebGPU didn't like fully ignore data races. It's just that these issues were a little subtle and they missed them in their specification. So because of that, we want to try and fix it. So we introduce what we call SafeRace Memory Safety Guarantee. It consists of two main properties. The first is called race-free slice, and it says program slices which contribute to memory indexing must be race-free. So if we look at this program here on the right again, there's two data races here. There's a data race between A and C and between B and C. And one way we can actually fix this using existing language constructs is atomics. So if we were to add a compiler pass which translates these accesses to atomic, you no longer have a data race in this program. And without a data race, you can no longer both optimize the min check away and have a situation where I of 0 returns 4 in instruction B. So that's the first property. The second property is called race interference, which says that data races cannot affect the behaviors of race-free slices of programs. And this actually follows on previous work by Dolan et al. From 2018, where they called this bounding data races in space. And unfortunately, this is not a property that can be implemented in WebGPU. It must be adopted by the lower level GPU frameworks. So what that actually looks like is if you see this code on the right here, now instead of indexing into M with I of 0, you index it into it with a local variable x, which cannot be shared between threads. However, this previous work showed that invalid compiler optimizations, you can end up in a situation where the x in B is set to 4, which would be bad because you read out of bounds if the min check was removed. So this property, race interference, prevents that from happening. Okay, so actually let's look at whether or not property 1 can be implemented, and if so, how do we implement it? So we did implement it in a compiler for WGSL programs using this memory logic on the left, and I'm going to walk through how we actually apply it to a program here on the right. So we'll start out by looking at this statement on line 9, which says var r equals b of x plus 1. In this case, that's represented as an access with an ID 7. It's a read access, and it's a read access to region B. And in this case, there is one what we call index dependency, and that's because x is used to access into B. Now, if we look at the definition of property 1 over here on the left under applying SMSG, we see that we say for all accesses y in an access's index and control dependencies, we must make the region associated with those accesses atomic. So in that case, we can go look at the index dependency here, which is access 6. This access 6 is the access to x itself, but again, x here is a local variable. So it actually cannot be shared between threads, so we don't need to make it atomic. And we can make it, we can mark it as safe. And this is actually where property 2 becomes important, because now we can say that because x can't be accessed by other threads, it cannot be affected by races on different memory locations, and so it is still a safe variable without even having to make it atomic. Now we're not done yet, because if you look at the second half of the property 1, it says that for all accesses z and an accesses y slice, we also have to make regions associated with those accesses atomic. And we define a slice as the transitive closure of the union of an access's index, control, and data dependencies. So basically what we're doing here is a backward slicing algorithm through our program. So in this case, this access to x on line 9 has 2 data dependencies in the program. The first is this access 5, so we're going to consider that one first. So in this line, x is set to 100. Again, we've already marked x as safe here, so we don't need to do anything. But we do need to consider its slice. In this case, it has a control dependency on access 4. So if we follow that back, we end up at this line 6, which says a of 0 greater than 5. Now, if you actually look at this program, this is dead code. A of 0 is set to 5, and it's not set to greater than 5 by this thread, so this if statement is actually dead code. But if the dead code were not removed and there was a data race on a of 0, it could end up executing, which could cause x to be set to 100. And if you had removed the min check or the clamp, then you would have an out-of-bounds access. So we actually have to mark region A here as atomic, and then you'd go through a forward pass and translate all those accesses to atomic accesses. And we're not quite done. We have to consider the data dependencies of this operation, and that is just this access on line 4. But again, we've already marked A as atomic, and there's no dependencies here, so we can return. The last access we need to consider is 3, which is on line 5 where you initialize x. But again, we've already marked x as safe, and it has no dependencies. So in this case, this program is finished with the analysis. And finally, because region B was not used in any of these dependency graphs, it can be marked safe as well and doesn't need to be made atomic. So that's part of the interesting kind of aspect of this property, is that it doesn't just mean you have to go through and translate everything to atomic. You can kind of do it in a more fine-grained way and still get the guarantees that you want. Now, what is actually the feasibility of this program, or of this analysis and this compiler pass? It turns out that it's actually works pretty well in WebGPU. And the reason for that, one, is that WGSL programs are single source. So you have all your dependencies up front when you're performing this analysis. You're not trying to rely on linking or any sorts of complex behaviors like that. The other is that inputs to programs cannot alias. This is one of the requirements of WebGPU. If they could alias, you're basically out of luck. You'd have to translate everything to atomic, but because of this, we have a little bit of freedom. However, there are some limitations to our approach. For example, there are no atomic floating point types in WGSL yet, although hopefully they will be added soon. So our analysis and our guarantees are not complete. If you use floating points in control or data dependencies, then you might end up in situations where you could read out of bounds accidentally. And I think the other thing to kind of mention here is as WebGPU develops, it might end up with more complex behaviors, but I think it's important to consider that we might want to keep the language constrained in some of these aspects. And there's actually precedent for this in other areas. For example, there's MISRA-C for safety critical environments. And I think WebGPU, as it evolves, is going to have to keep thinking about these types of issues and keep constraining itself. So the other thing that might come up, and did come up as we were implementing, is that, okay, we're translating accesses to atomic, and we're adding these like kind of restrictions on what data races can do. So what is actually the performance impact of that? So the first thing we did is we evaluated the performance of property 1. Basically, once we've done this kind of atomic translation, what is the overhead on existing programs? And it turns out that on the applications we considered, only 2 of them actually had any runtime overhead due to our pass. And so, of course, you could probably construct pathological programs where this is really bad, but we showed that on many, many important WebGPU applications, complex shaders that use very sophisticated optimization strategies, you still don't end up with a runtime overhead. And it turns out that's because these shaders don't really have complex dependency access patterns, and they're very amenable to the type of static analysis that we support. The second thing we did is we actually checked whether or not current implementations satisfy property 2. And of course, this is experimental and empirical, so it's not formal, but we use a bunch of metamorphic fuzzing on programs, and we find that in pretty much all cases, property 2 seems to be supported by current implementations. We found one issue, but it turned out to be an unrelated compiler bug as far as we're aware. So yeah, that kind of shows that potentially these properties could be adopted by current implementations and the WebGPU specification. So in this paper, I introduced SafeRace, a set of threat assessments and language proposals to address security concerns in WebGPU. It highlights the challenges of using accelerators in security critical environments, such as browsers, and it showcases the need for more research on compositional language design. And it was presented by me. I'm a PhD candidate at UC Santa Cruz. Feel free to reach out through my website or after this talk. And I'm also on the job market this year, so also reach out if you have or hear of opportunities. Thank you.
So we do have time for a couple of questions. Please go to the microphone.
Interesting project, interesting talks. Thanks so much. You know, when we make a variable atomic, we get 2 things. One is atomicity, the other one is ordering. So is there a way to figure out which one we need, and if we need ordering, can we insert fences at the right places?
So yeah, I glossed over that in the talk, but we use a relaxed atomics completely. There's no need for any ordering in this situation. So we're mainly worried about the atomicity and coherence properties of the atomics versus the ordering kind of things that they provide too.
So this might be a bit of an ask, but you found a bug because there was this sort of mismatch between the 2 interfaces. Have you thought about establishing the absence of, I'm thinking specifically of compiler mappings, where you think purely in terms of
Yeah, I think that's kind of where this all broke down to begin with. And the reason for that was like the undefined behavior in the lower level frameworks. So like WebGPU tried to give some semantics to data races and thought about all the compiler kind of paths that they could take, but the undefined behavior, of course, will always come back and bite you. So I think it'd be a bit controversial, especially for C++, but my kind of opinion there would be that these lower level GPU frameworks might want to remove undefined behavior completely, because then you might be able to do this kind of proof. But I think in the current situation, you're always going to be able to find these paths for other types of undefined behavior too.
Okay, thank you.
Last very quick one.
Yeah, you need source code to do all this analysis. Is there any cases where you don't have the source code and you have to do it without having source code? I mean, close libraries.
Luckily another reason, WebGPU, it all is kind of compiled in the browser at runtime. So you do have all the source code at that point. that's something, if they want to add that in the future, some sort of closed source libraries or binary formats, they're going to have to think about that. Hopefully this work helps them think about that.
Okay.
Okay, thank you so much.